Hey guys, so this is homework 9.3, and this is part 2 where you're supposed to follow along with the video and fill in the information. So dependent events. What dependent events are, or what it means is that when one event occurs, it could change the probability of another event occurring. So let's write that down. One event occurrence changes the events, the probability of another event occurring. And independent events are basically just like the complements. It means that one event occurring does not affect the outcome or the probability of another event. Okay, so let's look at example 1, and we're just going to decide if we think it's independent or dependent. A person pulls a red marble out of a bag that has 5 blue and 7 red marbles and does not replace it. Then a person pulls out another red marble. Is the probability of pulling the second red marble out dependent on pulling the first red marble? Okay, well, let's think of this. So I have a bag full of marbles. 5 blue, 7 red, so it's a total of 12. The probability that I pick a marble that's red is 7 out of 12. If I don't replace it, then that means there are only 6 marbles left, assuming I got a red one on the first try. So now the probability would be 6 red marbles out of 11, because now there's only a total of 11 marbles. So I would say that this is dependent. I would say that it's dependent because pulling the second red marble is dependent on whether the first one you pulled was red or not. Okay, so now let's take a look at an example where we kind of calculate or use probability to calculate if events are independent or dependent. Okay, so let's take a look at example number 2. So in example number 2, it says the spinner below is spun once and its outcome is noted. Let E be the event of getting an even number. Okay, so E stands for even. Let P be the event of getting a prime number, and let L be the event of getting a number less than 5. Find the following probabilities. Let's just review. Even numbers, I think we all know. Numbers less than 5, we all know. But prime numbers, maybe we forget. So let's take a look at the spinner. One thing people generally forget is that 1 is not a prime number. So the only prime numbers on here would be 2, 3, 5, and 7. Just so we know, we'll keep that to the side. So part A, the probability of getting an even number. Okay, so let's look at the spinner. And there are 8 numbers altogether. How many are even? We got 2, 4, 6, and 8. So 4 out of 8 are even, so that gives us a probability of 1/2. The next thing says the probability of getting an even given that the outcome was a prime number. Okay, so this is what we talked about yesterday. Conditional probability, where we have probability of something given this circumstance. So probability of getting an even given that the outcome was prime. Okay, so first thing we do is probability of even and prime over the probability of just being prime. So probability of even and prime. Well, let's see. Okay, so let's see. All of the prime numbers, we said that there were 4. And the numbers that are prime and even are is just the number 2. So it's 1 out of 4. There are 4 prime numbers total, and the numbers that are even n prime, there's just 1 of. The number 2 is the only one. Okay, let's keep going. So part D. Which event does E depend on, P or L? How can you tell? What is a reasonable test? Okay, so, oh, we skipped C. Or C and D are backwards, I think. Let's see. Yeah, let's do C, sorry. The probability of getting an even given that the outcome was a number less than 5. Okay, so probability of E given L. Well, the top should be the probability of E and L. The bottom should be the probability of just L. So the probability of being an even number and less than 5. Well, let's see. Even numbers less than 5. All the numbers less than 5 would be 4, 3, 2, and 1, and there are 2 even numbers. So this would be 2 out of 4. Okay, and then the probability of being less than 5, just less than 5, would be a total of 4. So we have 2 fourths over the number 4. Sorry, let's back up for a second. Probability of being even and less than 5. We just want the total number of things that satisfy that. So even and less than 5, so we said there's 1, 2, 3, and 4. So there's only 2 numbers that fit that, so it would be 2. Probability of being less than 5, there are 4 numbers that fit that category, so it's out of 4. So this is just 1 half. Okay, now let's move on to D. Okay, which event does E depend on? Does it depend on P or L? How can you tell? What is a reasonable test? Okay, so let's think about this. So if you look at the problems we just completed, part A was just the probability of E, and then we added in a given. So in part B, we did the probability of E given P. Then in C, we did the probability of E given L. So if you notice, part A, we got 1 half. And then part C, we got 1 half. So those are the same exact probabilities. So when L was introduced as a condition, E given L, it didn't change the probability. But when P was introduced as a condition, what was P? P is the event of getting a prime number. That affected the probability and changed the probability from 1 half to 1/4. So it appears that E depends on P, because of the fact that P occurs changes the probability of E. Whereas when L occurred in part C, it did not change the probability. Okay. I believe we have one more question to do. So let's keep going. So what we're going to do now is we're going to fill in a general formula for definition of independent events. 2 events, A and B, are defined to be independent if another if. So if we look back at that last example, the way that we knew that E was dependent on P was because when we did E given P, it was a different probability from just P of E. But when we did P of E given L, it was the same probability as P of E. So part A and part C were independent of each other, whereas part A and part B were dependent on each other. So here's our kind of like rule. If the probability of A given B is equal to the probability of A, then they are independent events. If the probability of B given A is equal to the probability of B, then they're independent events. Just 2 ways of like thinking about it. So I want you to just notice what's going on. It says the probability of A given B should equal the probability of this first letter A. That tells us that they're independent, the probabilities are the same, they didn't change. if the probability of B given A is equal to the probability of B. So again, B was the first letter here. Just two ways of looking at it, two ways of thinking about it, two different ways of writing it, just to show you the pattern here. Okay, so let's do one more example together. So let's read. A survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table below, sorted by gender. Okay, so all across the top I see different subjects, and then along the side I see female and male. Does it appear, based on the data in this table, that the preference for math as a favorite subject has a dependence on a student's gender? Show the analysis and explain your findings. So we want to know if liking math has anything to do with gender, being female or male. So we're going to use this kind of like rule or formula we just came up with. We want to see if the probability of liking math given you're a male, or the probability of liking math given you're a female, is the same as just the probability of liking math. So we're going to calculate three different probabilities. The probability of liking math, the probability of liking math given you're a male. So I'm just going to write in male so we didn't confuse the two M's. And the probability of liking math given that you're a female. And if either one of these are the same as the first one, or they're all different, then that tells us about independence or dependence. Okay, so first, probability of liking math. Okay, well, there are 18 people total who said they liked math, and that is out of 57 people total. So that's about 0.32. I'm only using rounding to decimals just so I can compare these three quantities. Okay, then I'm going to do probability of math given that they are a male. So remember, when it's a given, it's a conditional probability, so the top should be the probability that they're a male and like math, which is 10. And then the bottom should be the probability that they are just a male. So all males total is 27. Okay, so this is approximately 0.37. So far, I can tell that once I introduced this given condition of being a male, the probability changed. So I see that there's some dependence. Let's check for females. Okay, the probability of liking math given that you're a female. So the numerator should be the number of people who like math and are female. So that would be 8. And the bottom is just the probability, or the number of people who are female, and that is 30. Okay, and then this is approximately 0.27, also a different number. So if you notice, all three of these numbers are different. So what that tells us is that probability of, or liking math is dependent on gender. Because of all the people that liked math, it was 0.32. Or probability of liking math in general is 0.32. But once you said you have to be a male, then it's 0.37. Once you said female, 0.27. So it changes based on that. So if you go back to that formula, what we're saying is the conditional statement should just be equal to the probability of the first thing in order for them to be independent. And that's not happening here. None of the probabilities are the same. So it seems that liking math is dependent on gender. Okay, very last question we're going to do together. Does it appear, based on the data in this table, that the preference for social studies as a favorite subject has dependence on the student's gender? So basically the same as the first question, but now we're looking at social studies. Okay, so let's go through this. So I know I need three different things. I need the probability of liking social studies, the probability of liking social studies given I'm a male, probability of liking social studies given I am a female. And if any of them are the same, that will tell me that there's some independence. If any of them are different, that's dependence. Okay, so probability of just liking social studies in general. So we go to social studies, there's a total of 19 people who said they preferred social studies out of the total, which is 57, and that is approximately 0.33. Then it says probability of social studies given they are male. So when we do this conditional probability, I do the probability of both happening, social studies and male. So where does that intersect? Social studies and male, that's 9. Out of the probability of just male. So total males is 27. Okay, and that is approximately 33. Ooh, same number. All right, let's do the last one. Probability of liking social studies given they are female. Okay, so again, when it's a given, like social studies given female, it's conditional probability. So I do the probability of both happening. Social studies given they're female, which is 10, out of the probability of the total number of females, which is 30. And this is approximately 0.33%. This is approximately 0.33%. So, okay, so we are doing, okay, so what did we say, 10 out of 30, so that is again 0.33. So if you notice, all of them are the same. So when I just say probability of like social studies versus like social studies given you're a male or like social studies given you're a female, none of the probabilities change. So here's an example where probability of social studies given male is equal to the probability of social studies. And probability of social studies given female is equal to the probability of social studies. When that happens, that means that the events are independent. So there is no dependence between gender and liking social studies. Okay, that's all for now, guys. So we will work on 9.4 tomorrow. All right.